Hello and welcome back to Introduction to Number Theory. For further studies, we'll need an estimate on the number of poppings into an interval. So let's take rather small number, positive number beta. We do not so far define what small means, just beta greater than 0, and an interval of length L, which is of course also positive, and it will be greater than beta. Let's suppose it's much greater than beta. So there is a line, an interval of length L on this line, and the grasshopper, whose step is beta, and it jumps along the line, well, beta and beta, and at some moment it pops into the interval, and it goes on within the interval, and at some moment it pops out of the interval and continues its path. So we want to estimate the number of points, marked points, inside the interval within this visit. So let's denote the number of points by x, and say that the number of intervals, the number of small intervals between two marked points within the great interval is equal to x minus 1. So we can say that x minus 1 multiplied by beta, which is the distance between the first point inside the interval and the last point inside the interval. This distance is by all means less than the length of the interval. So we can say that from this it follows that x is less than L over beta plus 1. At the same time, if we consider the last point before the interval and the first point after the interval, the distance between these 2 points is equal to x plus 1 multiplied by beta, because the number of small intervals is equal to x plus 1, and it is greater than L. So from this it follows that x is greater than L over beta minus 1. So we gain finally an estimate on the number of points inside the interval. It's somewhere between L over beta minus 1 and L over beta plus 1. Well, here we consider jumping along a line. The grasshoppers in Kroneker's theorem and in Weyl's theorem are jumping along a circle, but every part of the circle can be considered as a line. So further on we will use this conclusion to estimate the number of poppings into an interval on a circle. And now, once again, imagine a circle and the grasshopper jumping along this circle. The length of the circle is equal to 1. This is the beginning of the circle. We denote it by 0. And this is the end of the circle. We denote it by 1. This is not 10. This is 0 and 1 separately. And we have a grasshopper jumping with constant step beta, which is greater than 0, and it is of course irrational, but it doesn't matter now. And this grasshopper, it starts from the 0 point and jumps and jumps and jumps and so on and so on, and on the next turn and on the third turn and so on. And we will now consider not necessarily the first time it passes the circle, not necessarily the second time, but arbitrary turn around the circle. So the grasshopper at some moment jumps on the circle and then continues and so on and so on. And somewhere on this circle we have an interval which we're interested in. We're interested in the frequency of getting into this interval. So our grasshopper carelessly jumps to the interval. At some moment it jumps into the interval. And at some moment it jumps out of the interval. And eventually it jumps out of the circle, out of the turn of the circle. So let's denote by C the number of marked points on the circle. And let's denote by I the number of marked points on the interval. All of these within one turn around the circle. So C is for circle, I is for interval, and what we wish to know is what can we say about the fraction I over C, which is something like the frequency of being inside the interval within this turn. We can use our previous inequalities over here to state that the number of marked points on the circle, well, C, is between 1 over beta plus 1 and 1 over beta minus 1, where 1 is the length of the circle itself. At the same time, I is the number of marked points inside the interval. I is between the length of the interval over beta plus 1 and the length of the interval over beta minus 1. So by combining these four actual inequalities, we can gain an estimate for frequency of grasshopper inside the interval. So let's divide I over C. It is less than the upper estimate for I over lower estimate for C, right? So since I is less than this expression here and C is greater than this expression here, we need to divide this by this. So we will get obviously the length of the interval plus beta over 1 minus beta. And to get the lower estimate for I over C, we need to take the lower estimate for I and divide it by upper estimate for C. So and this is what soon will help us prove the Weyl's theorem.